Hey everybody, it's Chief Meteorologist Brad Panovich. Today, Tuesday the 12th, we're going to talk about density. Density is one of those things that plays a huge part in weather and atmosphere, really understanding how the atmosphere works. Sometimes, when we think about the atmosphere, it's made up of gases. It's something we can't always see or feel or touch all the time, but it behaves a lot like a liquid in some way. So understanding how density works can really help you understand a lot of how weather works and how air movement occurs, and why some things happen that we see in meteorology. So today, meteorologist Chris Mulchahy is going to talk about density.
Density. Density is pretty much how compact an object is. The higher the mass of an object, well, the higher the density. For instance, iron is very dense. A rock, very dense. A feather, not really dense at all. Today, we're going to talk about how density, though, affects the atmosphere. How a density of a parcel is going to allow it to rise or sink, and also how temperature, pressure, and relative humidity can affect all the above. So mathematically, what is density? Density, we can represent it as D, or the technical term is this symbol, which is rho in the Greek alphabet. Rho, or density, equals mass divided by volume. And what I think is really cool about this is sometimes it's tough to remember these formulas. If you look at the M and the V, you can make a little heart out of it. So mass divided by volume. So thus, the more mass that we have, the more dense it's going to be. So that's usually why whenever you have really heavy things like iron and a rock, that is going to have a lot higher density. That means that there's a lot more molecules per unit of volume. But in the atmosphere, it's really a measure of the number of air molecules. But to complicate things more, air density is a little bit different. That formula is actually P, as in pressure, divided by RT. Now, the R is just the universal gas constant. That's getting a little bit too in particular, but there's also another formula that can come out of this. This is all part of the ideal gas law, and if you rearrange it, you can also get what the pressure formula is, which is just going to be density times that R constant and T. The reason why I show you this is it just really shows that as far as density goes, it's all related. Pressure, density, and temperature all work hand in hand for the changes in the atmosphere. For a better visual, here are two boxes. So which one do you think is more dense? If you guess box B, you are correct. The reason why is that there's a lot more air molecules in a given area. That's the same way that the atmosphere works. Whenever you have a lot less air molecules, that means that they're freely moving around, and likely that area of air, that parcel of air, is going to be a whole lot dense, and it's going to rise up. In this case, this would be warm air for box A, and cold air would be box B. Because in the colder environment, there's going to be a lot more of those molecules all huddled really closely together. So the warmer the air becomes, those molecules are able to move a lot more freely. The colder it becomes, those molecules will slow down and oftentimes will contract and huddle a little bit closer together. So that's the main reason why cold air is denser than warm air. Okay, we're done with the math, I promise, but let's do a little experiment that's going to show you exactly what densities do when they interact with each other. This is going to be a good demonstration to show what happens in the atmosphere, because densities are constantly changing throughout the atmosphere, and the bigger changes they have, well, the more unstable that environment gets. But let's take a big step back. Let's talk about liquids. Okay, what we have here is just a plain glass of water. The other liquids that we're going to be using are some maple syrup and some vegetable oil. Now, all these have different densities. The higher the density, well, that means that that liquid is going to settle down to the bottom. So I have water in there right now. Let's differentiate between everything by just adding a couple of drops of food coloring. It just makes it look so much better, right? All right, so let me do that little mix. All right, so there's the blue. That's the water. Let's pour in a little maple syrup. And the key word is I'm only going to do a little maple syrup just because I don't want to waste it, because I need this for my pancakes. So if you look really closely, there on the bottom, everything is settling out. But now let's do the last liquid. And a lot of times you need this to settle just a little bit more. Watch what happens when we pour the vegetable oil. Let's let this sit for a little bit. All right, now that it's settled, pretty cool, right? Well, you can see that maple syrup right on the bottom, just chilling right there. Meanwhile, you have water that's right on top. The reason why, water has a lower density than that of maple syrup, so it's resting on top. But then you wouldn't think about it, but any oil, vegetable oil especially, has a lower density than water. So now as that all settles, each one is in their own respective density layer. So if you look even a little closer, you can really see the difference of all of the different densities as they set up. That creates different layers, and the same thing happens in the atmosphere, but this is mainly based on pressure, but density is related to pressure, that there's also different layers of the atmosphere. On top of just the liquids, you can also drop other things, like this screw, and since that is super dense, that went all the way down to the bottom, but other things like a ping pong ball, well, that's going to rest on top because that has the lowest density of everything here. Now, other things you can do is also experiment by throwing different things into the different liquids. Right now, I'm just throwing in little bits of pepper. That floats on water, so that means that its density is higher than that of the vegetable oil, but it's less than that of the water, so that's why it floats. And that's a good rule of thumb. Anything that's floating on the water will usually have a lower density than that of what the water has. The most important thing you need to know about weather and density is that warm and moist air rises because it's less dense. On the inverse, cold air and dry air is more dense, so thus it sinks. So like the example that I drew at the beginning, the higher the pressure, usually the denser the air, and that's exactly what's happening. So as the density of a column of air increases, so does the pressure that it exerts on the surface. Just as you're seeing right here. I actually got this from one of my old college textbooks, but that warm, less dense air is able to move around a lot more freely. That is lower pressure. Since it's not constricted and not all bound together, it's able to move freely, rise up as that warmer air is rising up through the atmosphere. As for the colder air, it's usually pretty frigid and bonded together pretty well. And this is what air that you would typically see maybe moving in from the northwest, from Canada would look like, compared to the pink column is usually that southwesterly air that will flow into the area that will allow us to warm up and oftentimes lead to some thunderstorms if we have enough moisture. Now, I'm not going to go into great detail about the explanation of this since we already went into the ideal gas law, and that was already a little bit too much. But the difference in densities is also one of the reasons why we have different levels of clouds. Different parcels of air, and when I say parcel, I just mean a chunk of air as it's rising up. Depending on its density, it's going to condense at different levels, and it's going to stop rising depending on what its density is. Also, since density and pressure are related, the change in density ultimately leads to the change in pressure, which leads to wind. So there you have it. Density is so important in everyday weather, and it can change so quickly as the temperature rises or falls. I'm meteorologist Chris Mulchahy. I look forward to seeing you next time.
Thanks, Chris. Yeah, great episode today talking about density. It really is. We got a little math in there. I love that. And it just goes to show you a lot of what we do in meteorology is a lot of math. I was just talking to someone today about, wanting to go into meteorology, and what is the one thing that will surprise most people when they look into going into this field is how much math you need to take. High-level calculus, trigonometry, differential equations. Everything in the atmosphere is actually calculated using math equations. So it makes a lot of sense that we would have the ideal gas laws in there. So at any time, you can go to our website, WCNC.com, or go to our YouTube channel, WCNC's YouTube channel, and we have a playlist, every single one. This is episode 46 today. Go back and check them out. They're going to stay there. So maybe later this summer or in the fall when we get back to normal, you want to pull up some of these videos to teach a lesson. They're all listed in there.